So now we're going to see how to apply those ideas that we saw previously for reinforcement learning, but for deep reinforcement learning, which is when we use deep neural networks as part of the agent for deciding what to do. So I'm going to give a brief introduction to the motivation and deep reinforcement learning, and we're going to look at this trade-off between exploration and exploitation as we learn. Because the idea here is now that we're going to train the agent. The agent is basically this neural network that tells us the expected outcome of each action so that we can choose how to act. But we need examples for that. And to find examples, we're going to explore the game by playing the game. We're going to see learning policies that eventually end up being a bit confused with one another depending on the approach. And we're going to see a first example, the card problem, which is the tutorial for this week, and then I'm going to talk about the second side. So far we saw that if we know the Markov decision process, so if we have all the information about state transitions, the actions possible at each state, the probability of transitions, the rewards for all the states and so forth, we can compute the state value function for a policy. This is that function that tells us the expected discounted reward given a policy for each initial state. And we also can compute the Q function. The Q function is the action state value function that tells us for each state what is the value expected of each action, given that we are otherwise following some policy. Now, using these, we saw how to improve the policy by going back and forth between these. Now, unfortunately, this requires knowing the complete Markov decision process, so we need to have the information for all the states, and this generally is not possible because we would need to be able to enumerate all the possible states, all the possible action states combinations, and so on. So sometimes we have states that are too large. For example, consider this the breakout game. Even if we realize that this is a discrete set of states, because we have pixels, we have individual positions for the ball, the different bricks and so on. The number of combinations here is huge, and we cannot expect to compute all the tables for all the states and the expected rewards and so on. Or we can have problems that have a continuous variable. So these, we cannot simply enumerate all possibilities. This would be, for example, the cart pull problem, where the actions are pushing the cart a bit to the side, one side or the other, so we are applying a force and we are accelerating the cart. And what we need to do is to keep this pole balanced and prevent it from falling. So here the states are continuous because we can apply the force, and in theory, in practice it will be discrete because of the precision we are using on the simulation, but for a real game where we would have the computer play, for example, with a real card pull, then it would be discrete. And so we have infinite states and we cannot enumerate them all. So here we can combine these ideas that we saw previously with deep learning and solve this problem with the neural networks. Now, the features here when we are using deep reinforcement learning would be that we have some delayed feedback. We cannot look at the whole Markov decision process, but we have sequences of states and actions, and eventually we get rewards. So once we have that information, that can be used to propagate or to inform the network about the rewards. In supervised learning, we know the ground truth and we know the target. So, and if we look at how the network trains, that must always be the case, because we are always doing stochastic gradient descent to optimize some measure. So we need to have the target for each example to train the network. However, in reinforcement learning, what we are seeing is some estimates of the reward. So we are figuring out the examples as we play, and we have these estimates of relative values here that are appearing as we get feedback from the game. We also do not know the complete decision space, because we only have a sample of what possible moves there are and possible states in the game. And usually in deep reinforcement learning, we need to do some feature extraction. For example, if we're trying to learn to play a computer game by looking at the image, you need the network to extract the required features in order to learn what would be the expected outcome of each action. So these are usually the features in deep reinforcement learning. And one thing that we need to trade off in, or to calibrate, is this balance between exploration and exploitation. The idea is that we can interact with the game, so we can play the game, and so we can set our agent playing the game even before our agent knows how to play the game. But by this interaction and observation, we can get examples to train the agent, to improve the agent. But should the agent exploit its previous knowledge, if it's already working, learning how to play the game, it can use the knowledge it gathered and decide on what would be, according to its estimate, the best action. And this allows it to play the game better, and so proceed farther in the game, explore better the game, in that sense that it's following longer sequences of actions before, for example, crashing or losing the game and so on. But it's always following the same recipe. So at some point, since we are using the network to play the game and to build examples to train the network, if we always use the network to play, then we are only getting examples following the network. And so we cannot explore different possibilities. On the other hand, we can risk different actions, play at random, and this would give us access to new states that we would otherwise not find if we always follow the agent as it is in some moment. However, if we are playing fairly well and sometimes we make a random move, we probably are going to make a bad move and lose the game early or something like that. So there is a balance here between exploitation, which is using the knowledge we gathered so far to play better, and exploration, which is ignoring the knowledge so far in order to find new things, new possible actions, and so on. So there are several algorithms for this. These are only a few examples. Epsilon greedy exploration follows the best estimated action, so it's exploitation following what the agent already learned, except with a small epsilon probability, and with that probability it will move at random. So basically imagine that 90% of the times you do what the agent thinks is the best move, 10% of the times you move at random just to see if there's something there. Decaying epsilon greedy exploration is the same thing, but we start with a larger epsilon and we slowly bring down the epsilon. So the probability of acting at random will decrease as we improve learning the game. Optimistic initialization is to give a high a priori value, expected value for all the actions in the game. So when we try some action and we find that it works bad, that will lower the estimate for that particular action in that state. But the other actions still have an optimistic initialization, so we're going to experiment with them until eventually they start all going down, but only after we tried a fair sample of them. Softmax exploration we can pass the Q function we are in a given state. We have this Q function, remember, is the state action values function. So for this state, it gives us the expected discounted return of each different action we can take. So instead of picking the best one, we can use these different estimates as the input to a softmax. This gives us a probability distribution that is higher on the higher scores and lower on the lower ones, but not zero. So we can then choose at random following this probability distribution. It favors the ones that we estimate are better, but it gives us some probability of choosing differently. Upper confidence bound is basically adding to the estimate of the discounted value of this action on state S, which is this Q function, a term that depends on the number of times we took this particular action on this state. So if you already tried this action a lot, then we are adding a small bonus here. If we never try this action or very rarely try this action, then we are going to experiment with it more often, at least until we find that it doesn't work quite well. So this basically favors actions that were taken previously with lower probability. So let's see how we can learn policies. Basically, what we want to do here is to train the agent to act in the best way possible. This would be the policy that gives the agent the information on how to act for each state that it can find itself in. We cannot use the same iterative policy evaluation algorithm that we saw before, because we don't have access to the complete Markov decision process, so we cannot use that algorithm. But we can use this temporal difference learning, which basically allows us to improve the state value function by looking at these differences between what we are expecting the state value function to be given the reward. We have this reward now, we have the expected value in the future with this state value function, but we can also compare this to what our estimate is for this particular moment. So this would be the expected return that we are, our estimate of the expected return, if we are in state t. And this would be the reward that we are going to get and the estimated discounted return when we are in state t plus 1. And if our estimates are perfect, this should be exactly the same. Because the estimating starting from this state, or taking into account the reward, and estimating starting from the next state, should give the same thing. However, if these are not the same, then it means that our estimates are obviously not correct, because there is a difference between estimating from this step or from the next step. So basically we can use this as a way to improve our estimates, and so we're going to improve iteratively our estimates for the reward by looking at the difference between making the estimate at this state or making the estimate from the next state plus the reward that we are getting. So this would be an idea of how we can improve the V function, and this is the state value function, the one that gives us an estimate of the discounted value starting from this state, and also how we can improve the Q function. It's basically the same idea. So we are making an estimate for the value of taking action A at time t when we are at state t. This would be our estimate of what would be the discounted expected return of acting A at state t. And this is what we can measure, the reward we get for taking this action now, and our estimate from the next step onwards. And if these two are different, then we need to improve our estimates of the state action value. So this would be the modification we do to the estimate in order to improve it. And this would be the iterative process of improving the Q function. Okay, so the SARS algorithm, basically, the state action reward state action algorithm will estimate the future action values, always assuming the same policy. So basically here we are assuming that we are following the same policy, and we use this difference to update the state action value functions. An alternative, the Q-learning algorithm, it does the same thing. So it's basically the same difference, but it's going to assume that from the future onwards, we're going to, in the next step, we're going to take the best possible action. So the one that maximizes the state action value function. Note that this would be whatever action the policy would require, this would be the best action according to the state action value function. So this is a slight difference. The idea is that SARSA is on policy because it's following the policy. Q-learning is off policy because in this step it ignores the policy, and just takes the best action next. This is a conceptual difference that in practice it's going to be a bit tough to distinguish, because suppose that our policy is to look at the queue function and take the best action. So this would be the same, because we always take the best action according to the queue function, and that's the policy we follow. Or suppose that we use two different models. One to do this estimate that is telling us how to act, and the other where we are trying to figure out this value. So this could be more like Sarsen, but then if we mix the two models, we fall here again. So I'm going to show a practical example of that, but this is just to tell you that we can conceptually distinguish the two. We are trying to estimate the future according to the policy, or assuming the best action, and this would be the main difference between Sarsen and pure learning. But then in practice, these things get a bit mixed, because our policy may actually just be following the best action and other different adjustments that we can do to the methods that's learned. So basically, what we're going to do in deep reinforcement learning is, originally we assumed that was this V and Q functions, which are basically tables. Okay, so we are telling this for each state action pair, this would be like a table. We cannot have these tables in more realistic problems, because the number of entries would be huge. So what we're going to do is to use a neural network to try to get an approximation of the queue function. Instead of having a table that tells us for each state and action what is the expected discounted return, we're going to train a neural network to tell us for each state and action what is the expected discounted return. And that network will capture what this table would be. So what we need is basically to associate for each state and each action an expected discounted return. One thing that we could do is to have an input to the network to be the description of the state and the action, and then the network outputs a value. That could be one approach, but this would be a bit cumbersome, because for each action we would have to present a different input to the network and run the network several times. So what is actually done usually is to have a network that has one output per action. All of these are linear neurons, because we are doing a regression. We want the network to approximate the expected discounted return. And the input is the state. So if we input the state into the network gives us a set of values. So for action 0, this is what we expect to get in return. For action 1, for action 2, and so on. And we have all of those. So this would be the typical architecture. We input the state into the network. The output is one value for each action, and it's a linear output because it's a regression. And then we use mean squared error or something equivalent to that to train the network in order to approximate the target values there. So the question now is, how do we train the network? What examples do we present the network? Because, as you can see, we are going to use the network to try to estimate the expected return for acting in this particular way, that state, but we don't know that. If we knew that, we would not need the network. So how can we find examples to train the network? So that is basically the big problem that we're going to solve to make this work, which is finding these input-output pairs. So basically, input is observation of the state, output is the value of some action. And then we need to get this first, some set of examples. So we're going to create these tuples that tell us the state we're in, the action we took, the next state, the reward, and whether or not we reach the terminal state. So this is basically what we saw previously for the frozen lake example. And this we can generate, for example, by playing at random or by doing something and get a set of examples. And now what we can do is to try to adapt this SARS or Q-learning to the way we're going to train the network. And basically it would be to get a target value for doing some action at state t. That is the reward we got here, plus the discounted value of going from the next state onwards. Where are we going to get that? We can get that from the network itself. It's not going to be very good at the beginning, it's going to be a bad estimate, but at least we are getting the reward right, because that's information we get from the game, and this will help us adjust iteratively and improve the estimates of the Q values. So basically, in SARSA, we would try to estimate the future discounted return of acting from the next state onwards by following the policy. In Q-learning, we would estimate the future expected return by taking the best possible action from the next state onwards. Again, if our policy is to take the best possible action, and usually we train the network to give us the expected discounted return for all the different actions, and then we play the game by taking the best one at each move. So in that case, the policy would be to use the best one, and this would end up being the same thing in practice. But conceptually, we can think of these two approaches. But the main idea here is that the target that we want to learn for this particular example is that if we are at this state t, we did action t, and we got to state t plus 1 and received this reward, we want to train the network so that when it gets to state t, for this particular action, it gives us this or this output, which is the reward plus the expected discounted return afterwards. Okay, so let's see a demo in the card pull problem. This is the card pull problem where at each action, at each play, we can decide if we apply a force of plus or minus 1 to the card. So this is just a difference in the direction. And as we apply a force to the card will accelerate in that direction, or if it's moving on the other direction, it will start slowing down. And the goal is to keep the pole within 15 degrees of vertical so that it doesn't fall down. If the pole gets too far, too big an inclination, then we lose the game and the game stops. And basically we get rewards for the longer we play the game. So if you want to do this, you can import the OpenAI gym. This is just to build our networks. This double Q is a useful structure that it works like a list. It's optimized for taking elements at the beginning or the end, but the main thing here is that you can set a fixed size, and as you append things, you can take from the beginning, append at the end, but if you append more things than the size, it starts discarding the older one. So you can store there a set of examples, and then as the game improves, you can keep adding new examples and discarding the old ones. And as for each batch, you can just sample randomly from those examples in the net. Okay, so this is how you make the card pull game. You can play the game with that environment. And now we're going to create the network for the Q function. So basically, we have this dense layer of 24, dense layer of 12, and then we have this output for the last layer, which is a linear layer with as many outputs as the number of actions that we have. Now some details here that are slightly different from what we used to do. This he-uniform initialization uses this function here. We saw some examples of this some lectures ago. So basically 6 divided by the square root of the number of inputs into that particular layer. And the authors of the tutorial say this works better. And then also this Huber loss. A Huber loss is very similar to mean squared error. But when you start going to larger values, instead of increasing quadratically, it increases linear. So this basically makes it a bit softer on the large outliers, and they don't have so much weight, but it's still nearly the same thing as quadratic when you're close to 0. So basically, it's a softer mean squared error here. But you can experiment with different parameters here if you want. Now this is the main part, which is for training. So this is the gamma, the discount factor, the batch size, And we create a mini batch by sampling from this double queue, which is the replay memory. This is also where we're going to put in examples. Now we have this, we create the current states. Remember that this memory is a set of tuples like this. The state, the action, the next state, the reward, and whether or not it's terminal. So we can create a list of states for this batch by looking at the first item of each tuple, and the next states by looking at the fourth item of the tuple. And now we are going to predict, so this current QS list is using the model to predict the value, the expected discounted return of each action for each of these states in our mini batch. So we have a prediction for what would be the value there. And we also use this prediction for the next state. There is one detail here in that there is a model that is being trained and the target model that is doing the prediction from the future onward. So it's like this one here on the next step. Okay, we can use this here. So it's like the one that we're using for the prediction after the next step is different from the one that we're actually training. This is done to help stabilize learning a bit, because if you use exactly the same model in these two, since this one is being trained when you do the fit here, and if you're training it and using it to predict, and training and using it to predict, the targets keep changing very quickly. So what they do is that they start with a clone of the model, and every 100 steps or something like that, they, where is it? Here. So every 100 steps, they copy the weights of the model that is being trained to the one that is the target. So the model used to predict what will happen in the future is like the one that we're training. It's a clone, but it's a bit lagging and only updated every 100 steps or something like that to keep the target a bit more stable and not force the network to shoot so much in different places. But these are the kinds of tweaks that you can do that make it a bit different than to figure out if this is Q-learning or SARSA, because we are making these, our policy is to use the best one, but then we are using something that is a bit delayed. So we're not going to be too much concerned about the specifics of that, because things in practice get a lot messier, but it's the general idea that is important here. So basically what we're going to do is to loop through all of these examples that we have in our mini batch. So that's the long line here. Okay, we're going to loop through all the examples in the mini batch, and then we are going to check if we reached a terminal state. So if we reach a terminal state, then the future reward will be just the reward we get now, because there is no future. We ended the game. Otherwise, the maximum future reward will be the reward we get here and the discount factor multiplied by the maximum that we get from the predictions in this particular state in all the future actions. So this would be the future QS list, which is that model that keeps a bit lagging and predicting for the next state that we found ourselves in. So this would be the future, and this is the discount factor, and this is the reward we got for this move. And now, this way, we can create the target values for our fit, which would be for all the actions in general are just the values that we have estimated so far. Because there is a problem here, is that our prediction is for all the possible actions. But the actual move that we made is only for one action. So basically our prediction will be exactly the same as we predicted so far. So we don't change the network for all the actions, except the one that we took in this particular move. And that one will be different, which is the one that we estimate here. So we are copying what our current network is estimated to be the discounted expected return for all the actions, and only changing the one that we actually took and saw what happened in the game. So we have this reward information plus the estimates, okay? And that's what's happening here. We are, for each particular example, we are going to get the predictions that we already did, and only change the one corresponding to this action. This is the one that we are estimating here. So we do this for all the mini batch, and then we fit we do one step of fitting, which is presenting all the current states and all the expected return for the different actions. And for each particular move that we have here, we tweaked the return for that particular action. So now the network is going to learn a bit to improve the predictions. Okay, so now we're going to do this, create our agent, create another agent that is just a clone of the original one. We just set the weight equal to the original one, and this is the one that's going to lag a bit behind. Now we're going to create the double queue with a maximum of 50,000 examples, and our loop is basically, we are going to reset the environment, so we start the game, and repeat this until we finish a game. So this is basically this loop while is play a game. And now we're going to move the game, choose a random number here, and choose an action. So the action can be of two types. If the random number is below epsilon, that exploration probability, we act at random. We pick one action at random from the possible actions. Otherwise, we are going to create an example from the current state that we have here, and we're going to predict the outcome, the expected return of all the different actions using our model. And then we're going to take the best action there. So the action will be the one that gives us the highest expected discounted return according to the current model. So basically here we have exploration, take a step at random with some small probability, and exploitation, or use whatever we learned so far otherwise. Note that this epsilon will start high and then eventually we start decreasing the action. So now we get a new observation, reward, done, and so on by taking a step. This is where we're actually playing the game. This environment is the game, the card pull game, and we say, do that action, and the environment tells us what happens next. So we have this example here, and we append this to the replay memory. Now, this is the part where we're going to figure out whether we train or not. So basically, if the length of the replay memory is larger than this minimum replay size, and we have taken a sufficient number of steps before the last training, or after the last training, then we do train. Otherwise, if we still don't have enough examples, we continue doing this, and playing, and playing, and playing, even if we finish, because this while loop here may make us close the environment, but then we can repeat this and keep doing this. Okay? So the idea is to check if we have enough examples and if we have weighted long enough, and this is something that you can tweak a bit. So remember that if we have thousands of examples and you play one move and you replace one on the example, on the list, you didn't do much change on the list, so you still have basically the same number of examples. On the other hand, you cannot get the network to improve a lot in each training step, in each mini batch. It just looks at a few actions, at a few states, and only improves a bit. So you also need to do lots and lots of mini batches to train the network. And basically, you need to figure out how to balance the two. How much time to spend playing, how much time to spend training the network here, and this can be done empirically to optimize this. Okay, so here we have the rewards, printing what is being done. Note that every 100 steps or so, we copy the model that is lagging, the one we use for predictions, we copy into that one the weights of the model that we're training. And then eventually this will start playing better. We start reducing the epsilon, start fiddling with the exploration and exploitation, and the network starts improving on training. So this will be the tutorial that I recommend that you do first during this week. And then the assignment will also be for reinforcement learning, but in this case, you're going to train the network to play the snake game. So the input will be the image of the board. There are different colors. The food is green. You can set borders here in gray. The background is black, and the head of the snake is white, and the body red. So you have these color images, and this is the input into the network. And the network will have to decide for each state the expected return of the different actions. So basically, the motivation is to train the snake player, but the actual goal is not so much to have a good snake player, is to learn about these things. So what I would like to do, and you have that file that you have to fill out like the first assignment. So you explore different networks, different ways of training, scheduling the training, playing the network, and so on. Understand these different problems, experiment with this, and basically learn a bit about this by doing this and getting some experiments. So grading will depend a lot on how you explain things and what you explore of these possibilities. And for those of you who did machine learning last semester, you know that my second assignment is usually something more open that you can explore and try to think about the problem. So it's the same basic idea here. To do this, I provide you with the game itself. You have this class or the snake game that you can initialize with different dimensions, different numbers of food items, the border, and this grass. I'm going to explain what is the grass. But then you have the step. You present one action and the game moves forward one step. The reset resets the game at the beginning. So basically, once you do the action, you get a return that is similar to what we saw in those tuples. The next state of the board, the reward, whether or not it's a terminal state. So if you add to this the current state, you have the tuple that we saw previously. There is also this info about the score and things like that you can also use, but this is optional, and so that will give you the necessary information. And the board state is a NumPy array, so you have height and width of dimensions, a depth of 3. It's just like a color image that you can use, and the snake tail is red, head in white, food is green, and the borders are gray. You can control the border thickness by using this n here. So the total width and white will be this width plus 2n and height plus 2n, because adding to the width and height of the board, you have this border here. The reason for this is that suppose you have a network that expects to take images of 32 by 32, but you want to experiment with different sizes of the board. Instead of having to redo the network and change the architecture and so on, you simply reduce the size and add a border, and you keep the images exactly the same shape. So this makes it easier to do this kind of experiment. Don't go too small because of the way I'm initializing the snake. Sometimes you can get errors if you try to squeeze too much, because then the tail doesn't fit. But other than that, it should be okay doing something like 14 by 14 or something like that. So what I suggest is that you use images of 32 by 32, and this would be the default 30 by 30 on the board, and plus a border of 1 on each side. That's most of the examples I give here. But you can experiment with other sizes if you want. There's also a problem that rewards are rare, because only once in a while do you hit the apple and get a reward. So one possibility, if you want to train the snake to explore a bit more, is to use grass. So grass is a small reward, 0.05 on each place. You can also make the grass grow. This means that at each step it will grow up this amount until it reaches the maximum. And this means that every move the snake does into a place it has not been before, at least in a long time, the grass has grown, it gets a bit of a reward. So this may help you if you want to train the snake to move around in the board, because one problem here is that it's very easy for the snake to learn not to kill itself, because that's a negative reward. But then it may learn just to go around in the loop and doesn't do anything else that may happen. So you can experiment with this and see what happens. One problem is also that if you play at random, the snake is going to die very often. So one way of giving it a better starting point is to generate a set of examples that also include successful moves, not dying, finding the apple, and so forth. So what you can do is to use a very simple heuristic, for example, going straight for the apple or something like that, to generate an initial set of examples. This will not be your agent, but this will just be to get a better set of examples in the beginning so that the agent starts learning. This is often used in training networks to play games because you can use examples from humans playing. If you have lots of recorded examples, you can start the network from there, and that will already give you a good starting point. In this case, you probably don't have the time to be playing lots of snake games, but you can create a simple heuristic, generate examples from there, and use that. So, if you want, you can cheat with this method, getState. That gives you the position of the head, the array with the coordinates of the tail, and the position of the apples. They can be more than one. So you get everything there, and you can build your own heuristic. But note that this is not for your network to see. The idea is to train the network to see only the board. This is a cheat if you want to just create a good set of examples to warm start the training of the network. This is some examples of a result. So basically, this would be using the heuristic to populate the initial pool of examples, and then starting to train the network, but then improving by also using the network itself to play games longer. So you see that we can have very long games. This is already 380 something without dying. However, at least my snake is not very good at finding the apple and roams around a lot until sometimes it decides to approach the apple and so on. But it can wander a lot here. It doesn't die, but it doesn't do much else. So this can take a while to train. You can experiment with different board size to fine-tune your code and so on. But basically the idea is for you to have a good set of examples and experiments so that you can discuss what things work best or not, what you think about each part is doing, how you implemented the code and so on, so that you can get a good discussion there. So you have the instructions on the course site and the code, but in any case I recommend that you do the cart pole example first, because even though the snake game is not on the gym, the output is similar to the one on the gym. So if you follow the cart pole tutorial, you already have a base for a code that works in a similar way before you move on to the snake phase. Okay, so to sum up, we saw deep reinforcement learning. Basically, the idea here is that we cannot have all those large tables for the Q function and the V function, but we can train a neural network to approximate those as best as possible. You need to balance out these two things during training, which is exploring new possible moves by moving at random or something like that, or using the knowledge acquired to try to play better and go farther in the game. Both of these are necessary. You need to balance them out. And now what we're going to do to improve things is basically to look at what our network is telling us is the prediction for this particular state. What would be for the next state after we do the move and get the reward at this particular state, and then trying to minimize that difference. So we're going to use that future prediction as a target to improve the predictions of the network. There are these two differences, which is when we are just looking at the Q function and taking the best action, or when we are looking at the policy, and that's the difference between SARS and Q learning. However, in practice, things get a bit more confusing because we can actually, our policy can be just looking at the maximum, or we can use different models with some lag for making the predictions and training and so on. So if you want to read more about this, I recommend these chapters 4 through 6 and 8 of this book. In fact, I recommend the whole book if you're interested in deep reinforcement learning. However, this is optional because for the grading and for the assignment, this is basically the information you need, is what I gave in the lectures. This is only if you're interested in this particular subject. Okay?